bending and stretching motions for a single piezoelectric beam. As you see, when we apply the voltage, V of T over there, it only affects the stretching motion but not the bending motion. So for the sake of a single piezoelectric beam, we're not interested in the bending motion, but we're going to be interested in the strongly coupled 2D. In fact, as a side note here, we used the Euler Bernoulli small displacement assumptions to derive the equations of motion, but if you want to go with the Minlin, Timoshenko small displacement assumptions, since we have only the stretching motions, you won't have a different set of equations for the stretching part of it. In fact, if you include the bending motion for a 3-layer beam, then obviously the bending equations are going to change because the rotation is going to take into effect, right? But for the sake of this problem, we're not interested in the bending motion at all. So in our case, we're more interested in the stabilizability of piezoelectric beams by applied control. So if you want to choose a state feedback controller, if you look at the non-magnetic models, we always have mechanical type measurements. In other words, mechanical type sensors, like we put a laser sensor at the end of the beam, at the tip of the beam, and then measure the velocity or displacement. But when we include the magnetic effects, we immediately get electrical measurements. So interestingly, on this topic, we have a lot of papers popping up in the Google. If you write stabilizability of a piezoelectric beam, you will see more than thousands of papers, and in fact more are coming. And for the sake of our talk, we're interested in B-star type feedback. And some of you know that B-star feedback is a physical feedback, and then most of the engineers go with this type of feedback. So as I said, in this case, the B-star feedback is electrical, but not mechanical at all. So, and in fact, you will see that the B-star feedback is the total current accumulated at the electrodes of the piezoelectric beam. So a few more comments on the way. So we proved this theorem in the 2013 CDC paper that for certain choices of material parameters, B-star feedback does not make the system strongly stable. So that was an interesting property because what we know about the classical or standard theory for piezoelectric beams is that when you supply the mechanical feedback, the system is exponentially stable, but all of a sudden, with the inclusion of magnetic effects, we get no stability result here. So that was sort of like the big difference between the classical electrostatic approach and the fully dynamic approach. And this sort of like tells us that material parameters are very important in terms of the obtention of the stabilizability of piezoelectric beams. So as a side comment here before I move on to the next slide, I would like to say that the material parameter combinations generally correspond to high frequency modes. So for practical applications, if you're working with the low frequency eigenvalues and eigenmodes corresponding to that, so this would not be a problem because for those modes we will most probably achieve a stability result of some sort. But whenever you go to stabilizing electromagnetic vibrations, then you run into the problem of having no stability for certain choices of material parameters. And another paper popped in the 2014 Cyan paper. In fact, we proved that not only B-star feedback makes the system not stable, but also any type of state feedback makes the system not even exponentially stable. So this is a strong property because adding a minor effect that you think is minor may cause a big problem at the end because you want to stabilize the system for all modes, but in turn you get no stability with any choice of feedback. And another paper, this was a sole author paper of myself that was published in NCSS, that we can recover exponential stability for certain material parameters. So at the end of the day, everything boils down to a number theoretical approach that for certain combinations of material parameters we recover exponential stability or some sort of stability, but for some other combinations of material parameters we lose the stability all the way. So this shows that when you add the magnetic effects, the stabilizability problem strongly depends on the sensitivity of the material parameters.